look at it in my office. All right, so just to recap, because my phone went off, X-rays and gamma rays have the shortest wavelength. Waves are measured from one spot on one wave to the exact same spot on the next adjacent wave. That's a wavelength. So electromagnetic radiation, even though it travels at the same speed, each energy level has a different wavelength. And looking at the spectrum, radio frequency, longest wavelength, X-rays and gamma rays, the shortest wavelength. And they kind of overlap, and so it's continuous. So we've got sine waves, we've got wavelength. The other thing is we've got travels in waves, and it has its own special frequency. Okay, just the word itself, not applying it to anything. What does frequency mean?
Like how often something is.
Bingo, how often something happens. Frequency, if you have an increased frequency, what does that mean? Happens more often, exactly. So now we've got sine waves, we've got frequency. And if we take the waves themselves, we bunch them up together like that. Then we've got our wavelength on the waves on bottom. What can we say about those waves? Okay, well, backing up to wavelength, what can we say about it?
They're shorter.
They're shorter, right, they're shorter wavelength. So comparing these two, what we've got, again, if we draw a line through these, we've got a shorter wavelength, and we've also got a decreased amplitude as we go by down the line here. Amplitude would be the measure of the height, okay? And for our purposes, it really doesn't matter. Amplitude is just a word that, you know, we use to talk about the measure of the height. So in the energy levels of electromagnetic radiation, for our purposes, amplitude doesn't mean anything, but it is a word you need to be familiar with. Amplitude, amplitude. Y'all have no idea how difficult it can be to talk while you're writing, and I'm a miserable speller anyway, so you know that's just an excuse. So we got wavelength, now we've got frequency. What speed does electromagnetic radiation travel at?
Speed of light.
Speed of light, right. So if it's all traveling at speed of light, and if I could take this thing, and let's say my drawings there were three-dimensional, and if I could take it and let's say that I could push these things off of the board and they just kind of disappear. If I could push them at a constant rate, because all electromagnetic radiation travels the same speed, that being the speed of light. So if I could push it at the same rate of speed, then which one would have the highest frequency? The one on bottom, right? How often a wave would be pushed off of the board would be your frequency, right? So the one on bottom has a higher frequency. So when we're talking about wavelength and frequency, since electromagnetic radiation all travels at the same speed, same velocity, what can we say about wavelength and frequency?
They're inversely related.
They're inversely proportional, right? So as wavelength goes up, our frequency goes down, right? As wavelength goes down, our frequency goes up. Okay? Y'all get that?
Say that one more time.
As wavelength goes up, you increase wavelength, frequency goes down. As wavelength goes down, frequency goes up. Okay? So the difference between them is it, anybody need to walk through that again? Because it's important that you get this before we go on. Because there's three things that we've got to cover in this. I don't want to press on to you're on board for this.
Frequency increases, the wavelength decreases.
Right. As frequency increases, the wavelength decreases. As wavelength increases, frequency decreases. Right. Okay? So the difference between all of these the different levels of electromagnetic radiation, then become energy. How much energy does each one carry? All right? So looking back over at page 49, you can kind of see the graphically, if we just pay attention to frequency and wavelength, notice that frequency all the way at the bottom is 10 to the second power for radio frequency, right? But what is wavelength?
10 to the 6th.
10 to the 6th power, right? So that 6 just represents the number of zeros you would add to the end of 10. Same thing with 2. So where your frequency is 200, that would be what? 10 million would be your wavelength. So very, very long wavelength, very low frequency. But looking at the opposite end, what you see is 10 to, we're back into X-rays, gamma rays, therapy doses. 10 to the 24th power would be your frequency, but what is your wavelength?
Negative 16.
Negative 16. Very, very, very short wavelength, very high frequency. Okay? Now, we're going to add energy into that. So if you look at the next column over where you see energy, and that's measured in electron volts, it's really pretty much the same thing as kilovolts or kilo electron volts. So voltage, electron volts, volts, really the same thing. So if you apply the basically KVP to that, if you look at the bottom, what is your energy level of radio frequency?
Negative 12.
Negative, yeah, negative 12, which means it's very, 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 very low energy, okay? As opposed to X-rays, gamma rays, and therapy doses, all the way at the top, what is it?
High energy.
It's very high, it's extremely high. So, what we can say about wavelength, frequency, and energy, wavelength and frequency are inversely proportional. As one goes up, the other goes down, right? So as energy, as wavelength goes up, frequency goes down. As frequency goes up, wavelength goes down, right? Now let's make a correlation with energy. So which one is proportional to energy? Frequency or wavelength? Frequency, right. So as frequency goes up, energy goes up. Okay, so the energy and frequency are directly proportional. They go in the same direction, right? So they're directly proportional, and both of them are inversely proportional to
Wavelength.
wavelength, right? Okay, so is everybody on board for that? There's several questions in the worksheets that cover that. I want you to get home and say, okay, what do you say about that? Okay. So all travel in the same. Somebody.
No, sorry, it's clear my
That's
throat.
okay. Okay, so all traveling sine waves all have frequency, being how often the wave passes, and all have traveling sine waves. That's just the length of the wave. That went easier than I thought it would. Okay, so mathematically, what we have is the wave equation, which is frequency is equal to. Make sure I'm not inverting this. No, yeah, velocity, duh. Velocity is equal to frequency times wavelength, okay? So I believe in simplifying an equation for demonstration purposes wherever you can and not complicating it, throwing a whole bunch of big numbers at something, the 10 to the 24th power and stuff like that, it'd just be too much, right? So velocity, if our velocity is always the same, then we can throw any number at it and it doesn't really matter what that number is, right? So velocity we're going to say is 1, okay? 1 speed of light. So if velocity equals 1, then we can work with these two numbers knowing that they're inversely proportional. As one goes up, the other goes down. Essentially we can throw anything at it as long as it equals 1, right? What's the simplest thing to multiply against something to make it equal 1? 1, right. So 1 times 1, okay? So what if then we change our frequency to 2? Then in order to keep this mathematically correct, what will we have to do? Hmm?
Change our.
Change that to,
Oh.
we doubled this, so that has to be
0.5.
0.5 or 1/2, right? So, 1/2. So is that a true statement as well?
Yes.
So mathematically also, what you have is an inverse relationship. As one goes up, the other has to go down. If we flip that around and made wavelength 2 and frequency would have to be 1/2, right, right. So inversely proportional is what we're looking at between frequency and wavelength. Okay?
So in a problem, velocity would always be 1? Is that what you're saying?
No, I'm just, first off, I'm not gonna have you work the wave equation. That's just a mathematical representation of what we just saw.
Oh, okay, so.
And that is as frequency goes up, then wavelength has to go down. If wavelength goes up, then frequency has to go down. Yeah. Okay. So, yeah, that went a whole lot better than I thought it was gonna go. I cut onto that quick. All right, so the electromagnetic spectrum, we talked about that. It represents a lot of different energy levels. We go from radio frequency all the way up to X-rays and gamma rays. It's gonna be a short day. So where do we use these? Well, we're gonna use several of them. Some we don't really want to use, but we have to deal with. And some we have to use. All right, so starting at the bottom, well, let's start with what you're most familiar with. How do we use light in X-ray?
Invisible light.
Visible light, right. So what do you use visible light for?
Collimation.
Very good, collimation. First off, you gotta see the patient, right? You ever tried to take an X-ray of a patient in the dark? I hope not. It'd be kind of creepy to start with, but it'd be pretty impossible as well. Okay, so you got an X-ray tube coming off of the bottom of the X-ray tube. You got a collimator housing, and I'm going to draw that bigger. Okay, so you got X-ray tube, and you've got collimator housing. Now your X-ray tube is up inside of this protective housing. We'll talk about the importance of the protective housing later on. But what we've got is 2 electrodes, right? In the X-ray tube looks something like this. And we've got this thing that spins around and around. We call that the rotating anode, right? So on the opposite end, what we've got is filament. We call that the cathode, right? So the purpose for the X-ray tube is to accelerate electrons from the cathode to the anode to create X-rays. When you turn your light on, I told you that the X-ray tube is basically a great big complicated expensive light bulb, right? And it is. But as we're going to learn later in the semester, the other things that are inside this housing would prevent the light that comes from this to be emitted through the housing, okay? So you got some stuff inside, you got some oil inside, and we'll discuss the intricacies of that later on. It's got a port here where the X-rays exit, the X-ray tube and the tube housing. So you got this exit port, but that's usually metal. When's the last time you shone light through metal? Never, right? So can this light escape from there, and can you use that to adjust your collimators? Answer is no, you can't. So what we've got inside the collimator housing, and this is not drawn anywhere close to scale, this thing's gonna have to be huge. What we've got inside of the X-ray housing, if you looked, what you would see is not a light, but you would see a mirror. You don't see the light.
Oh, have
actually looked in one without
Did
the
you?
light on. I was like, oh, that's cool.
Yeah, so there's a mirror inside there, and that mirror is at a perfect 45-degree angle. It should be at a perfect 45-degree angle. What you've got off to the side is a light bulb, okay? So you got a light bulb, maybe incandescent, maybe LED, doesn't really matter, but you got a light bulb. The purpose for the light bulb is to shine a light directly into the mirror that would reflect the collimation, or the field size, okay? A few things that we need to understand about the light and its position as well as a mirror is that, again, electromagnetic radiation has some of the same properties, right? So if you emit X-rays from this point source right here, we send electrons across the tube and we smack into this thing, then what we're going to do is we're going to create electromagnetic radiation just like we would create electromagnetic radiation right here. You turn a light bulb on, it's like a globe type light bulb. Where's the light go? Everywhere, right. That's what we call isotropic. Okay, big word meaning equal intensity in all different directions. It's not on this test, but you need to file it away somewhere. Isotropic emissions, that's what we get when we hit the anode with the electrons from the cathode is the isotropic emissions from the target. They go off in all different directions with equal intensity. Okay, so they're going all over the place. The only ones that we're interested in seeing are the ones that are coming down through the port. Okay, so these have to be diverging, or they are diverging at a specific rate. Now, if I had two flashlights and I was shining side by side an area yay big on the board, I had two flashlights and I was shining them side by side. I took one of them and I backed it up. What would happen to the light field on the second one? It would increase, right. Also, if I were to take one of the light bulb or the flashlights and I would put it at an angle, what would I see in my circle? Would it be a perfect circle? Mm-hmm. No, it would be a little bit of an oval, right? So what we have to have in this light field and its relationship to the radiation field is two things. One is that the distance between here and here has to be exactly the same as the distance between here and here. It's not drawn that way here because I couldn't make it work, but it has to be identical. Why does it have to be identical? Well, because if this distance is shorter, then what I get is a smaller projected field size or radiation size. So what you're doing is your collimators are not accurate, right? The collimator's not accurate, so you're exposing a larger portion of the patient to what you intended to expose. Does that make sense? Because they both diverge, because the electromagnetic radiation is the emission of the electromagnetic radiation both places is isotropic and it's going to diverge at the same rate, then this distance has to be exactly the same as this distance. That's number one. And number two is that this mirror has to be at a perfect 45-degree angle to make this light field reflect exactly like that one. Okay? If it slips, and now it's here instead of there, where's your light field going to be? Right? So you bang around your X-ray tube, you grab it and you walk across the room and you just let go of the locks so it stops real abruptly. One of the things that can happen is that mirror can slip. Now you've got a projected light field that doesn't represent your radiation field. Okay? So very important to be very careful with your X-ray tube so that doesn't happen, because now you line up a patient for a KUB with your light field over here, what are you not going to get? KUB. You might get 1K, and you're going to get a half a B, but you're not going to get KUB, right? So, perfect 45-degree angle, distance has to be the same. Distance between the focal spot and the mirror has to be exactly the same as the distance between the light bulb and the mirror. So what we use, first off, is visible light. So we use visible light in two ways. One, so we can see the patient, and the other one, so that we can know where to put the radiation field. We don't see the light coming from the tube. We see the light coming from a light bulb off to the side. Now, why can we not put the light bulb right there?
So they reflect up, right?
It would reflect up, but, well, if we didn't have the mirror there, why could we not just put a light bulb? Say going down like this, why could we not do that?
It won't be as intense, the light.
What's that?
That sounds to me.
Oh, I'm sorry, with the masks, I can't tell who's talking.
Like the light wouldn't be as intense because it's going all over instead
Okay.
of being directed.
The divergence would be different, is that kind of where you were going?
Yes, yeah.
The divergence would be different, it wouldn't be the same, that's number one. Number two, what glows in the light bulb?
The filament.
The filament, right? So every one of your x-rays would have this great big filament going across it, so can't do that. We have to use reflected light. Okay, so there's visible light. What else do we use? Well, what are we trying to create? X-rays, right. So we got X-rays when we accelerate the electrons across the tube, and this is where some of y'all will probably stumble a little bit on some tests at some point. Again, whenever we increase our kVp, we increase the energy level of the X-ray beam. Okay, so looking back at your spectrum there, the high energy X-ray photons are going to be shorter wavelength and higher frequency. Okay, but they all travel at the same speed, still being the speed of light, right? But when you increase your kVp, what you do is effectively change the charge in the X-ray tube. So this side becomes relatively greater negative charge. This side becomes relatively higher positive charge. Opposites do what? They attract. So the more opposites you have, the more attraction you get, and the faster the electrons come across the tube. Okay? So you do have some speed element whenever you increase kVp, but it's not in the X-ray photon, it's in the acceleration of the electrons across the tube. Okay? Again, that's later in the semester, but I wanted to point that out. Once they're created into X-rays, they become, or they travel all at the same speed, speed of light. So, the second type of electromagnetic radiation, and the most important type that we're interested in, are the X-rays, right? X-rays are created in two different ways once they hit the target. One is that they slow down when they go around the nucleus, and we call that Bremsstrahlung. Yeah, it sounds like you're going Bremsstrahlung, you know. It's brims, right? Slowing down or breaking radiation. The other is characteristic X-rays where we create those by hitting the inner shell electrons. Both X-rays. So we got X-rays, all right? Is there anything else we create inside of the X-ray tube?
Heat.
Heat, yep. We also create light, so we're back to light, but heat. The main thing that's going to destroy an X-ray tube and shorten the tube life is heat. So what is heat? Where does it sit on the electromagnetic spectrum? Right in the middle, yeah, like infrared radiation. So how we're going to deal with the heat and hopefully extend the tube life is with this oil. We'll talk about that later. We got fans that blow air across, and we'll talk about that later in the semester too. But the heat doesn't just stay right there on the target because it's in a vacuum. It's going to travel, so it's going to radiate down to the tube envelope. We'll call it tube envelope. It's just the glass and the metal, depending on what kind of tube you've got. So we got infrared radiation. We got infrared radiation as well. Okay, so in diagnostic, that's mainly what we're dealing with. So that's mainly what you're dealing with. But there is one other place that we're going to use, or actually two other places that we use different types of electromagnetic energy. One is in MRI. Anybody ever had an MRI? Okay. So you got a lot of stuff going on with the MRI. MRI doesn't use X-rays. It uses great big magnets. MRI stands for magnetic resonance imaging. And it uses great big magnets, and it uses radio frequency waves. So what you've got in an MRI machine is this great big tube that they stick you inside of, and it's basically a giant electromagnet, a superconducting magnet. And what the physics behind the MRI is that when you stick somebody inside of a magnet, if you've got atoms with unpaired electrons, unpaired meaning there's an odd number of electrons, 1, 3, 5, 7, and so on, then they demonstrate magnetic properties. So what's the most common element inside your body? What are you made out of? Made out of what?
Carbon.
Okay, carbon. We're carbon-based, but the actual,
Water.
yeah, there you go, water. So what's water? H2O. So the most common element inside your body is hydrogen. So what's the atomic number of hydrogen? That's helium. 1. Right, so it's got 1 proton, so how many electrons is it going to have? It's going to have 1, which means it has unpaired electrons, right? So they stick you inside of a great big magnet, and what happens is that your hydrogen atoms have a tendency to point in one direction or the other. They stick you inside, it just sounds like it's not good for you, but they stick you inside and your atoms go boop, like that, okay? Now if you've had an MRI, you hear all this pounding going on, and that's because you got an alternating current and your coils are flipping around, not your coils, but the coils inside of the machine are flipping around. That's what the banging sound is. But there's also a radio frequency that takes all those atoms and it slams them into a different direction. So it's kind of like, you know, they're happy, you know, buzzing around at just random. You stick them inside a big magnet and they go in one direction or the other. And then they set off a bomb that is a radio frequency wave and they slam in one direction, okay? Now they're gonna reorient with or against the magnetic field, but it's gonna take them time to do so. And that time is gonna be based on how much water is in the tissue, okay? So if anybody wants to share, what'd you have an MRI of?
My foot.
What's that?
My foot.
Your foot, okay, what was wrong with your foot?
I had a bad stress fracture in it.
Okay,
And it was really hard for the doctor to see in an X-ray, so they did an MRI.
okay, that's interesting. I would have thought of CT, but
Yeah, I don't know.
they might have been looking for some, you know, some soft tissue indicator. Anybody else?
Mine is my knee.
Knee? Oh, y'all are killing me. What'd you have going on with your knee?
It's for my ACL. But
Oh, good, thank you. ACL, what is ACL? Anterior cruciate ligament. So it's soft tissue. And somebody else?
My head.
Your head, so it was like a brain scan type thing?
Yeah, I was passing out and they didn't know why.
Okay, very good. So you're the odd man out. So, yeah, so where I was going with this is that MRI shows certain things exceptionally well and some things not so well. So whatever has a lot of water in it, it shows extremely well because water has a lot of hydrogen, and what MRI uses is hydrogen, right? So it doesn't show bones all that well, so he might have been looking for, you know, soft tissue.
I do have a question.
Okay.
So, if somebody like me, I drink water constantly, so would that affect your MRI if you're like really hydrated?
That's a good question. Possibly, you know, I wouldn't think appreciably, you know, but it maybe a little bit, possibly. I've never worked in MRI, so I don't know, but possibly. So what it shows is anything that has a lot of water in it. So soft tissue, it shows extremely well. Bones, mainly calcium, a little bit of water, so you can see bones, doesn't show them real well, okay? So we use radio frequency in MRI. In nuclear medicine, they'll use gamma rays, gamma emitters. We inject the patient with radioisotopes. in nuclear medicine and then measure how much radiation is coming off the patient. So how MRI works is it's really not intended to show anatomy, but rather physiology. So let's say you've got a thyroid problem. You don't know if you've got thyroid cancer, if you got hypothyroidism, meaning it doesn't work as well as it should, or hyperthyroidism, meaning that it works too well. So what they'll do in nuclear medicine is they'll take a tracer, a material that a particular organ system likes, so to speak, like thyroid would be iodine, and they'll attach a radioisotope to it so that that radiation goes specifically to that organ system and collects inside that organ system. So they know how much radiation should come off of a normal, within a variance, a normal thyroid. And if you're not emitting enough radiation, they know you've got hypothyroidism. If you're emitting too much, then there's some other pathology going on there, okay? So they measure the radiation that's coming out of it. So gamma rays, in a lot of cases, come out of nuclear medicine. Here's the thing that you need to understand about nuclear medicine is at some point you're gonna have to go over to nuke med. And it might scare you half to death, okay? So, because radiation, you're thinking it's radioactive and it's bouncing all around the room. That's not exactly true. The patient does emit radiation, so you're gonna have a tendency to wanna do what?
Stay away from them.
Stay away from them is number one. Number two is put on an apron, right? You may go up to a patient's room sometime, and what you'll see is, sign on the door saying the patient had a nuclear medicine scan or something like that. So you're gonna have a tendency to put a lead apron on to go up to nuclear medicine. The problem is that if you wear a lead apron, in a lot of cases with a patient who's emitting high energy gamma rays, you might cause, by wearing a lead apron, you might cause an increase in radiation dose as opposed to not wearing a lead apron. So the X-ray creation in the target here is electrons creating X-rays through brims and through characteristic interaction, right? But inside the patient's body, the same things are going on. If you eject an electron from some sort of tissue inside of the patient, a characteristic X-ray is created inside of the patient with X-rays, okay? Same thing happens with gamma rays. The difference is that gamma rays are going to exist in a higher level than what we're going to use in diagnostic X-ray, and therefore it's going to create a lot of exposure. So you put on an apron, and the apron becomes an X-ray tube, okay? So you get a lot of interaction inside the apron that results in the apron becoming an X-ray emitter, and your dose actually goes up if you wear a lead apron in nuclear medicine. So if you ever walk over to nuclear medicine, what you're not going to see is anybody wearing an apron, and that's why. And likewise, if you put on an apron, your dose is going to increase, okay? So important thing to understand there. So what we use in diagnostic are those three, but in X-ray, in the overall imaging department, we also use those too. Now you might have a tendency to think, well, what about ultrasound? Well, the answer is in the word. What is ultrasound? Sound waves, right. So how fast do sound waves travel?
Slower than speed of
A lot slower than speed of light. So they travel at about 750 miles an hour as opposed to whatever ridiculous speed it was that we put up here a minute ago, 3 million meters per second, right? 300 million meters per second, whatever it was. So, all that. Any questions? All right, well, we're going to pull it up there, so we're a little bit early. And we'll probably finish up on Wednesday. I'll try to remember to put airplane mode on.